Here are the sample problems for Math 117, Class 13. This first one is designed to show you the difference between what happens when you have a single random variable between 0 and 1 and you have an infinite sequence of such random variables. There are two problems just like this on the workshop problem for this class. So I'm going to draw a diagram to represent this. That's the index n, and I'm going to do values 2, which means our marathon runner is 2.5 hours away from her 5-hour target. 3, which means she's 5/3 of an hour. 6, which means she's 5/6 of an hour. And 12, which means she is 5/12 of an hour away from her goal of running for 5 hours. And at each of these checkpoints, her total distance traveled is in a certain range, between 24 minus 30 over n and 30 minus 24 over n. So that means that when n equals 2, she's run somewhere between 9 and 18 miles. When n equals 3, she's gone somewhere between 14 and 22 miles. When n equals 6, she's somewhere between 19 and 26 miles. When n equals 12, now she's within half an hour of her goal. She's somewhere in between 21 and 28 miles. And in the first scenario, we're going to pick a random variable, omega, in between 0 and 1. So our sample space is just 0 and 1. And let's suppose we pick something that's around omega equals 1/2. Then she goes from there to there to there to there. So this is case 1. In case 1, the sequence of random variables x sub n, her positions at n equals 2, 3, and so on, converge to a random variable x, and the limit random variable x is uniformly distributed in the interval from 24 to 30, because you can see if you look at the formula for x sub n, in the limit where n approaches infinity, the lower limit of the interval goes to 24, the upper limit goes to 30. Well, if a random variable is uniformly distributed in the interval from 27 to 30, clearly its expectation is 27, and we can work out the expectation of the random variable x sub n. For example, when n equals 2, the random variable is uniformly distributed in 9 to 18, and more generally, its expectation is the average of the lower limit and the upper limit of the interval. In other words, it's 27 minus 27 over n, and that converges to 27. So this is the case where the sequence of random variables actually converges to a limit, and the expectation of the limit is equal to the limit of the expectations. Now let's think about this in a little more detail. we pick one omega and it applies throughout the run. And the sequence of random variables, real numbers now, because we're evaluating a specific element of the sample space, converges to x of omega. That just means if omega is 1/2, her sequence of positions eventually converges to something halfway in between 24 and 30. Now, Fattoush Lemma talks about the lim inf, but when a sequence of real numbers has a limit, the lim inf and the lim sup are both equal to the limit. So that limit is just the limiting random variable x evaluated on omega. If we look in more detail about how we calculate the lim inf, though, what we are told to do is to look at all indices m greater than or equal to n. Look at x sub m of omega. And as you can see, the smallest of those values is always her current position. While if you look at the supremum over n of all the values remains constant at the final value. So the supremum of x sub m over omega is just x of omega. This is characteristic of increasing sequences. Okay, so that's all there is to case 1. Fattoush Lemma applies because what Fattoush Lemma says is that the lim inf of the expectation is always greater than or equal to the expectation of the lim inf, and in this case the two are equal. Now let's look at case 2. In case 2, the sample space is going to consist of infinite sequences of real numbers, all between 0 and 1. So that says when n equals 2, we may generate a rather large value of x2, and she's there, then she's there, then she's there, then she's there, and she finally ends up there. She actually could end up running backwards from time to time in this scenario. This is a more interesting case because although the sequence of random variables doesn't converge to anything, the sequence of expectations still converges. And in fact, the expectation of x sub n is the same as in the previous case. We look at n equals 6, for example, and say she's equally likely to be anywhere between 19 and 26. Same as before. The only difference is that where previously we had a fixed value like 1/2 that applied to each of these intervals, now we're generating a fresh one for each value of n. Okay. In that case, the limit is still equal to 27, but now x sub n does not converge. What's going to happen is there will be values jumping around in these intervals. As n gets larger and larger and she gets closer and closer to finishing, she will jump around between a total distance of 24 miles and a total distance of 30 miles. However, although x sub n omega is not convergent, it doesn't have a limit, any bounded sequence of real numbers has both a lim inf and a lim sup, and it's easy to figure those out. For any value of n, and let's think about what happens when n gets large. Let's think about just for large n, there will be values of x sub n close to 0 and close to 1. So what I can say is that the lim inf of x sub n of omega, that is the smallest value that's going to show up after time n in the limit, is going to be 24, because there'll be some large value of n for which x sub n is very close to 0, and the position will be close to 24. However, this is true only almost surely, because it's not impossible that we could keep generating values of x sub n that are all in between 0.8 and 1, never getting small values. The probability of that is 0, but it's not impossible. Similarly, the lim sup of x sub n of omega is going to be 30, because for some large value of n, we're almost certain to have an x sub n that is very close to 1. But again, that's true only almost surely. So now we can check Fattoush Lemma. Fattoush Lemma says, look at the lim inf of the expectation of x sub n and compare that with the expectation of the lim inf of x sub n. And Fattoush Lemma says the left-hand side is always greater than or equal to the right-hand side. Let's look at the left-hand side in this case. The expectation is getting closer and closer and closer to 27. We can say the smallest expectation that's going to show up after n has become very large is 27. On the other hand, if you look at the lim inf of xn, that's going to be 24, and indeed 27 is greater than or equal to 24. The way I like to think about Fattoush Lemma is that Fattoush Lemma says the worst case of the expectation is always greater than or equal to the expectation of the worst case. Here we have on the right the expectation of the worst case, because we're looking at individual values of x sub n and saying we're going to get some of those that are very close to 0 and get at the left endpoint. Okay, we'll move on to number 2, which is substantially more straightforward. So, here our sample space consists of all positive integers. The sigma field is 2 to the omega. That's uncountable, but manageable. And the probability function looks really weird. The probability function that I have chosen is P of the value I, and I'm going to sum this, is the sum of 6 over pi squared I squared. So let's sum this from I equals 1 to infinity. That's 6 over pi squared times 1 plus 1/4 plus 1/9 plus ... This series was summed way back when by Euler. It sums to pi squared over 6. So the probabilities do indeed sum to 1. Let's make a little table of them. When I equals 1, the probability of 1 is 6 over pi squared. The payoff for 1 is plus 1, and the product of the two is 6 over pi squared. When I equals 2, the probability is down by a factor of 4. The payoff is negative 2 now, and the product of those is therefore minus 1/2 times 6 over pi squared. For I equals 3, the payoff is plus 3, and the product of the probability and the payoff is plus 1/3 times 6 over pi squared. And now you're getting the general idea. We get a negative payoff if the value is 4, and payoff times probability works out to minus 1/4 times 6 over pi squared. Now, the following is true but irrelevant. If I sum the products in the last column, I get 6 over pi squared multiplied by 1 minus 1/2 plus 1/3 minus 1/4 plus ... And this infinite series converges conditionally to the natural log of 2. So as a statement about infinite series, this is true. But it is irrelevant for our purposes. We never use conditional convergent series to calculate expectation. So now let's do it right. The right way to do this is first we calculate the expectation of the random variable x plus, which is x if the payoff is positive, 0 otherwise. And that means we're just going to use the positive terms in the payoff column. We get 1 plus 1/3 plus 1/5 plus 1/7 plus ... That doesn't converge, it diverges to infinity. And then, if we take x minus, which is the absolute value of the payoff if it's negative, 0 otherwise, we'll get 1/4, 1/2, 1/6, and so on. That also diverges to infinity. And our conclusion is that the expectation of this random variable does not exist. Now, if you think about this as an actual game, this conclusion is realistic. If you and I are playing this game, and I agree with you that I'll be a nice guy, and if a large odd number turns up, I still won't make you pay me any more than $1,000. So if I bound it below, then this is a very good game for you. Now the expectation is actually defined. And it's plus infinity. If, on the other hand, I say, we're going to play this game, but I've only got $1,000 with me today, so in the highly unlikely event that an even number bigger than 1,000 turns up, I'll give you $1,000. Is that okay? Don't take that, because in that case, the expectation is minus infinity. If we bound it both above and below, say we'll take anything bigger than plus or 1,000 or anything more negative than minus 1,000 and convert it to plus or minus 1,000 respectively, then everything is well defined. We've got a simple random variable, and the expectation will be very close to this value. So the moral of this is, when you have non-positive random variables, split them into positive and negative parts. Don't write down conditionally convergent series to do expectation. Well, this has gone on so long, I think I'm going to stop this video here and put the proof on a separate one.